A warm welcome to our studio guests today and to fellow travelers out in cyberspace. Thanks to that non-stop stream of zeros and ones. My name is Peter Gobetz, co-founder of the Zero Project and moderator of the International Conference/Workshop on Zero. The Zero Project is a three-stage affair. There's a book project, an associated online event, and the in-depth research program to follow. Today, session number 18, two contributors to the monograph on Zero book project who joined most recently, Professor Jim Ritter, Sorbonne Université in Paris, on Zero in ancient Mesopotamian mathematics, and Professor Friedhelm Hoffmann, Ludwig-Maximilian University of Munich in Germany. He will speak on the absence of zero in ancient Egyptian mathematics. Our panelist today is a speaker from an earlier session, Dr. Marina Will, who can judge on zero in modern mathematics. As such, we have gathered at least the two most ancient civilizations who have played a role in the zero story. And we may be joined by others later on in the program. Because if there's anything we've learned so far, there's nothing that meets the eye. Our focus will be on the distinction between the placeholder zero and the number zero. And Jim, we are most keen to learn about the subtleties of Mesopotamian zeros, plural, because we understand that there were several. Would you please introduce yourself briefly and then proceed with your presentation?
Okay, thank you, Peter. My name is Jim Ritter. I was a professor of mathematics at the University of Paris 8. I'm now retired, but I have always done my major research in the history of mathematics, history of physics. I'll be talking today about the question of the zero or zeros in ancient Mesopotamia. And I think I'll be beginning now. I will be working mainly with slides because there's a lot of material that needs to be looked at. And it's difficult to describe in words, but it's rather easy to see in pictures. So that's what I'll be doing. Perhaps we could have, right, okay, thank you. So the zeros of Mesopotamia, we'll be looking at actually two different histories, two different stories in this talk. They both stretch over a long period of time, from the end of the 3rd millennium BCE until the end of Cuneiform civilization itself in the 1st century CE. The story of the development of the two types of placeholder zero, there were already two zeros involved there at least, and the story of nothings in Babylonia, that is, how did Babylonians talk about such things, as the result of subtracting one number from itself, there where we speak of the number zero. I have a little time chart on the timeline on the bottom there of the screen, which you can see with the names given by seriologists to the different periods of time that are involved in the years that you see below. All dates are in this talk will be BCE, of course. So starting about 2300 with the Or-3 period and running down to the Seleucid or Macedonian domination period in Mesopotamia, which runs almost to the end of the almost the beginning of the Common Era. And I'll be talking about two different domains of knowledge. One is mathematics, which arises in terms of its main development during at the end of the Or-3 period in the early part of the Old Babylonian. And it is at this time that the sexagesimal positional system, that is base 60 and positional by place system is put into effect. It runs until the end of the Seleucid period, and also mathematical astronomy. This is late compared to mathematics. It comes into being in the Achaemenid and Seleucid periods, that is under Persian and Macedonian domination, in the second half of the 1st millennium BC. So let me talk about my tablets. I can see that there's some problem in in the actual setting up of the slide. I don't know if anything can be done about that. But in any case, well, one can see pretty much what I was talking about. Cuneiform writing is an important part because we're looking at cuneiform tablets. So what I have here is a tablet, a rather elaborate tablet from the Ur-3 period. We'll be actually seeing it briefly again later on. And just to show you the way that tablets work, they are two-sided essentially. The obverse has in here has 3 columns. Sometimes they just have 1. Sometimes they can go up to 6 or maybe even more, 12 columns for some of the astronomical texts. You read them left to right, like English, and top to bottom in each column. So you begin at the left, and you read here in the upper left-hand corner, you read down, and then you go to the second column and so forth. You flip it over through an axis through the center, and you have the reverse, and there the columns are read in reverse order, starting at the right, still reading each line left to right until the end of the tablet over here. And we'll be looking at numbers, of course, so we need to look at how cuneiform numbers were written. I'll be talking about the sexagesimal system, as I said. You must remember this sexagesimal system was a very restricted writing system. It was not the common way of writing numbers for ordinary people, at least those who could write. It was used in schools and in scholarly communities. It was set up in this way. The numbers from 1 to 9 were written by essentially an additive form of these vertical wedges. The numbers from 10, the tens from 10 to 50 were written by using the corner wedge, or Winkelhaken as our German colleagues call it, and which is often used in non-German speaking discussions as well. And the way that they're put together is this way. That is, I've written here 29, 52, 46, so that you have 2 10s, 9 1s, 5 10s, 2 1s, 4 10s, 6 1s. It's an additive construction using tens and units, and I've transcribed it as is normally done by using 2-digit decimal numbers running from 1 to 59, leaving 0 aside for the moment. And you'll notice that intermediate zeros, that is placeholders, only are important when you come to having at least 3 digits in your number. So that the middle digit can possibly be a 0, have no values in it. This is an important point because, in fact, 3-digit numbers are rather rare in early periods. They become much more frequent and much higher numbers of digits as well. But this comes with time, and I think is a deliberate choice of mathematics teachers to keep things simple. I've written here a number of numbers which I put in mainly because I want to show you what happens when you have missing units or missing tens or missing 60s in a number. So I've taken the same 29, 52, 46. Here I've dropped out the units in the first digit. So that's now 20, 52, 46. 29, 02, I've dropped it out. I've dropped out tens in the middle unit. I've dropped out ones in the first unit and tens in the second unit here. And here I've dropped out an entire sexagesimal digit. That is the middle digit of the 3. And you can see just looking at it that this causes blanks. So in a sense, if you didn't do anything, just wrote your numbers very carefully and always equally spaced, you would automatically have blanks, not only for the sexagesimal 0, but also for decimal and unit zeros. And this is, I think, an important point. There are difference between relative and absolute values, and 2 types of zeros, 2 types of placeholders are involved in this representation. Intermediate placeholders, which as I've already indicated in these earlier numbers, are the absence of a given digit between two expressed digits of a number, and the question of leading and trailing zeros before the digits that you're concerned with or after the digits you're concerned with, which indicate the absolute value of a number. Is it 100, 1,000, 10,000? I'm thinking of our system. And we'll hear about how that is done very easily in the Egyptian system. It's not done easily in the Mesopotamian system. It is only done easily in our system because we have rules about dropping out leading and trailing zeros. But in any case, I won't be going into this here because the question of absolute values is I won't have time to go into it. It will of course be discussed in the paper for the monograph. There are two types of mathematical text that we'll be looking at that involves a sexagesimal system. They were written for and used in school and in scholarly circles, and part of the training of each scribe consisted in learning how to solve problems by following established algorithms, step-by-step solutions. I call them solved problem texts, and also when needed text to calculate and use tables in the evaluation of the arithmetic steps of the algorithms, and these were written down on tables and on little clay tablets that were just scribbled on for calculations. I'll be talking about tables and solve problem text in what follows, and I just want to show you the physical difference between the two. Physical differences are important in my talk, and I want you to be able to see how that works out. On the left, you have a table. On the right, you have a problem text, or procedure text, I also call it. It's a multiplication table on the left. Both are Old Babylonian. Very simple. You one column, but arranged in two sort of sub columns on each side. This is a multiplication table of 30s, running where the multiplier is 30 and works on 1 down to 50 on the table. This is a standard way of doing tables. On the right, you have a mathematical problem text. There are 5 problems on this text. It's also a single column text, but as you can see, it's much more filled in. It's written linearly. It's written in words, which stretch all across the entire width of the column, so that you have a rather full tablet there. The mathematical text, problem text, and the table text are can be differentiated by the 2 columns on the left. I talk about table text, on the right, problem text. In the table text, as I said, the signs are arranged in subcolumns. In problem text, they're arranged linearly, so they're space filling. In the table text, blanks as placeholders are easily recognized because they're written in columns. On the right, blanks as placeholders in continuous writing, linear writing is subject to compression and therefore to disappearance if you're writing quickly. And finally, the entries are determined by a free choice of precision, the number of places that you're interested in the table text I've chosen. There's only one sexagesimal place used. And in the problem text, the entries are determined by the choice of numbers that you use as examples for the problems you're solving. So a free choice of parameters that are used in the problems. There was probably deliberate avoidance of internal sexagesimal placeholders, zeros, in early constructed texts, that is problem and table texts in mathematics. But this became impossible later on in the first millennium because with the arrival of astronomy, you had actual physical phenomena to model, and you were bound by empirical constraints, which did not allow you to simply make easy your mathematics and only deal with simple numbers, because you simply had to account for the actual rather complicated astronomical observations So in particular, with the development of mathematical astronomy in the first millennium, there was a flourishing of explicit placeholder notations in both astronomy and mathematics. My first example is an Ur-3 text, not a mathematical text, not an astronomical text. It's a simple, or what seems to be a simple, administrative text of silver receipts. I'll be looking at this part of the tablet. It's only written on one side. It's a 2-column tablet. I'll be looking at the top of the first column, and I've just shown that over here. Here it is in bigger form, and I've written out the numbers in sort of modern typographical cuneiform here on the right-hand side. You can see them rather easily. You can probably, with a little bit of familiarity, you can read them right off. And then you have 2 lines, essentially, of linearly written words and number signs, but number signs that don't come from the sexagesimal system. They come from a metrological system of weights. Here's on the left, the actual columns of the original of the text, and here is finally the translation into modern transcription. And in particular, the 2 lines here are simply give in the ordinary weight system the total of these of the entry for individual deliveries, which is 1.5 mana, 3.5 gin, minus 7 shea of silver, and marked as individual deliveries. What are these sexagesimal numbers doing on an economics tablet, on an administrative tablet? They don't belong on administrative tablets. What they're doing is that they are actually working out this line. They're working out a total. And what the scribe has done, and I've done, but is not written down on the table, he probably did it on a scrap piece of clay, was to add up these four 3-digit sexagesimal numbers, and you do it in the same way that we do our adding with tens, and you doing carrying across the columns. In any case, the answer is 1, 33, 27, 50. Okay, and that needs to be translated into the weight system. It's actually a rather easy translation compared to some, because weight system is a late system coming into Mesopotamian metrology. It is already rather 60-ish in its form. In any case, you can do that. You can simply translate it into the total, and the total of the sexagesimal numbers comes out to be exactly what is written in the text. And I just wanted to point out 2 blanks in this number, in the sexagesimal numbers. One is an empty column, because it's an empty sexagesimal placeholder, and the other is an empty units placeholder, as there are no units in the 30 in the 4th number, but you see the blank. These blanks serve as placeholders. They serve as placeholders. They're in a sense imposed by the way that you write down numbers, and if you do them carefully in columns, then you will automatically have blanks as placeholders. And these are, in fact, the earliest known use of blanks, both as a sexagesimal placeholder and as what I call a decimal placeholder. That is a placeholder that indicates there are no units or no tens in a given number. So you have the earliest known use of a sexagesimal placeholder and of a decimal placeholder, and that's simply partially because this is the very first examples that we know of sexagesimal writing, sexagesimal numbers. But the first use of a special sign for a missing digit or part of a digit occurs in the late Old Babylonian period. What I showed you was the late Ur-3 period. Now I want to go to the late Old Babylonian period around the 17th century BCE, and I want to leave Mesopotamia proper. I want to go over to the next country to the east in what is now Iran, and that is to Elam and to its capital Susa. Elam adopted under duress the Mesopotamian writing system, and indeed the languages, because they were conquered in the third millennium by Mesopotamia. And in particular, from the late Old Babylonian period, from Susa, we have mathematical texts. We have table texts, and we have procedure texts. This is a table text from Mesopotamia, from Susa, sorry. And if you could see, okay, so I've just written it's a table text of a special kind. It is actually a series of problems of a standard kind, which are arranged in columns, so that a teacher, for example, could choose to have numbers which make the problems come out nicely when you actually give them to a student. But the numbers, the results, the answers that are given over here to what happens when you add 1.5 times the length of a rectangle to the area, comes out to these numbers. And in this particular number, you see that there is a blank here and essentially a 0 here. I put this in because we've already seen blanks after all, but just to show you that in Susa at this time, for table texts, which are nicely arranged in columns, you are still using blanks for placeholders. Now I want to give you a mathematical procedure text. This is a problem with a given solution, step by step, working out of the solution. And here you have it. I'm not going to go into the detail of the text. I don't have the time here. This will all be done in the monograph article. But I only want to draw your attention to the numbers in the text and the ways in which they are. I have put a box around them, a blue box around them over here. And these are numbers in the same way that we've seen the numbers earlier. The only one difference is that they have this special sign here. Which is a sign that was called by the Babylonians gan, and it is put into the numbers rather frequently here, as you can see, and it has a special role to play. It is I will not go into that. It is a indication of zeros. It's an indication of zeros in here. Let me just do the next one down. I've indicated the function of the gan in each of these numbers by a different color key. Where you have a red number, the gan is serving at the same time as an indication for missing a placeholder for missing tens and missing units. Where you have a green, it's for missing tens only. Where you have a blue, it is for missing units. So that you have gan coming in as not as a number, because it is not one of the number signs. It is a special sign, a kind of diacritic sign, indicating there is a space. There would be a blank between the 20, for example, here, between the 20 and the 3, because if you wrote them too close together, you might mistake that for 23 and not 23. And the same for the other indications. Here you have it between 21 and 9, because you don't want to read it as 21 plus 9, 30. Okay, and so on. So you have the need for, in the procedure text, the need for a special sign to indicate that which a blank served perfectly well to indicate in the table text, and continues even in Susa to serve that purpose. But in the procedure text, you need something a bit stronger because you have this compression of numbers written much more closely together than you could afford to do on a table. And note that it is not obligatory. Here we have a number with a missing 10, but without any gan in it. So the sign gan can serve as a non-obligatory placeholder for missing tens and or missing units in Old Babylonian Susa. Note that we have no indicator from Susa of a missing sexagesimal system except the blank in the table text. There are no missing sexagesimal units in procedure text from Susa. Gan is not the only number you can also use at the same time, but from a different part of Mesopotamia, from the area north of Mesopotamia proper in the Dayala River region, from the city of Meitoran. You have a mathematical procedure text, equally Old Babylonian, and in which you have another sign, A, which the name for it is A, which occurs in numbers in the writing of the problem, and which serves as a placeholder for missing tens, and can also serve for missing units, by the way. So it also is a decimal placeholder, 0. And like gan, it is a non-obligatory placeholder for missing tens and units in Old Babylonian Meitoran. It's perhaps suggestive that both types of explicit 0D, my term for decimal placeholder, first arise in different peripheral areas of Mesopotamia. You can see that Meitoran here in the northern Yala, Susa over here in the Elamite East. And both of them, both the gan and the A, are used in Mesopotamian writing as a kind of separation sign normally. That is, it's used to mark, in other non-mathematical, non-astronomical texts, it's used to mark off spaces, glosses, comments, etc. in general cuneiform text, somewhat akin in purpose to our modern footnotes. So it comes from that repertoire. The choice in Elam and in Meitoran, a different choice in each case, but was made from the same repertoire of signs, from non-phonetic signs. Both these two signs, in fact, can be used also as phonetic signs, but that isn't where they come from in this particular usage. I just wanted to show A, for example, as a separation sign in a mathematical text from Old Babylonia. It is where you see this A sign appearing in numbers. But now it doesn't represent a missing decimal digit. It represents simply the fact that there are two numbers and they're written close together. And to keep them apart, you put it in as a separation sign. So 1430 A01 is really two numbers, 1430 and 01, the end of one line, the beginning of the next line in the algorithm. And the same thing went down here for this number here, two separate numbers. That's the A as a separation sign, even in mathematical text, but in Meitoran we saw it taken over to represent decimal placeholders. This use of placeholders is rare, but we do have later uses of it. Here's a Middle Babylonian text from around 1200 BCE coming in. It's I won't go into it. I will simply point out that it occurs in numbers again, and it once again represents decimal placeholder, missing units, missing tens. And so we have no explicit placeholder indicator sign for sexagesimal digits, missing sexagesimal digits, until we get down to the first millennium. And in around the 7th century, we have a text coming from Kish Neo-Babylonian text, which is shown here, and I'll be looking at one bit of its obverse, one bit of its reverse. It's a table text. It is a multiplication text, and a squaring text, and more specifically, it is multiplication, but of numbers by themselves, and written out explicitly as such. And it is a bit more advanced compared to earlier Old Babylonian texts, in the sense that instead of the Old Babylonian squaring tables have the numbers 1 to 50, 59, essentially, as single-digit numbers which are squared. This has two-digit numbers as well as single-digit numbers, and 15, 15 and a half, in fact, 1530, 16, 1630, and so forth. And when you write out the answer, unlike the single-digit squares, you actually have cases where there is a missing sexagesimal digit. For example, here, 15 and a half times 15 and a half, 1530 times 1530 is 40015. And we have this 30, the sign for 30, the numerical sign for 30, written as there, but it doesn't mean 30 in this particular tablet. It is a sexagesimal placeholder. It is also 30. Just two lines further down, you have the same three corner wedges serving as a standard 30 in the number, the sexagesimal number 32 here. So it serves its usual way as a number, but also as a explicit sexagesimal placeholder, and it is in fact the earliest known example of an explicit written sexagesimal placeholder. A spectacularly bad one, by the way, because since it is also a number, it is very easily confused with the 30s that are everywhere in this tablet. But it serves that purpose in this tablet, and it appears other places where it's very obvious to calculate and see that it is indeed a sexagesimal placeholder. On the back, we have another 4230 times 4230 with this 30 appearing, where it is actually serving as a decimal placeholder, like Gan and A in the earlier periods. This number here is to be read 3615, not 303615, or not 3000615. If it would be the case if it were a sexagesimal placeholder. This is another reason why it is a rather bad choice, but it was the choice made. And as far as we know, it's the earliest choice made for an explicit sexagesimal placeholder. Moving down to the Seleucid period, this last period of cuneiform culture in Mesopotamia, from Uruk we have a mathematical procedure text in which we have another explicit sign, much better because it is not a number sign, chosen to represent zeros, represent placeholders. We have them here. You see them quite often on the tablet, and they indicate zeros. They indicate placeholders, and they are particularly sexagesimal placeholders, and they represent the numbers with here where there are two of them written one after the other. They are actually two sexagesimal zeros, two sexagesimal placeholders. It also serves just for a single missing sexagesimal place in this number over here. Again, I won't go into the algorithm that will be discussed in the article. So we have now another placeholder. This placeholder, let me just go back to it a second. This placeholder, which doesn't have even a name as far as I know in ancient times, is not a number and is not even a sign separator in ordinary usage. It's two corner wedges put one above the other. Remember that 20 is a two corner wedges put one after the other. So this is not a number. It's not used any other place other than as a sexagesimal or decimal, and as we'll see in a second, placeholder. Here is an astronomical table text, lunar ephemeris, tables of lunar risings and settings from Babylon. This is a dated text very nicely, so we know it dates from before, or just before, probably 103 BC. And what we see in the table are again our double Winkelhaken, our double corner wedges here, and serving as sexagesimal placeholders. By the way, you see them here not as intermediate, but as leading zeros. I won't be going into this in this talk because that involves discussions of absolute valuations, and that will be in for the article. So as is the case for mathematical texts, this double corner wedge is also the standard placeholder in astronomical texts, both procedures and tables, until the end of cuneiform culture. There were essentially only two schools of mathematical astronomy in the first millennium BCE. One was in Babylon in the north, one was in Uruk in the south. They had slightly different rules. They were distinguished not only by some of the procedures they used to predict the future position of moon, the stars, and planets, but also by the fact that their use of the double corner wedge as a sexagesimal placeholder was slightly different. It was used only as a sexagesimal placeholder in Babylon, but it was used both as a sexagesimal and decimal placeholder in Uruk. There are a few exceptions in both directions for these two cities, but that was essentially the rule. So just putting the whole sort of first part of my story together about placeholders, I have here the sort of table with the dates, with the sexagesimal placeholders not arriving until around 650, the decimal placeholders from very early on in the old Babylonian period, of course blanks before then, and even to some extent during the period when other signs were used, explicit signs. You have decimals and sexagesimals, usually the same in many cases, until you get down to the double wedge, double corner wedge, which is, as I said, always sexagesimal and can be decimal in Uruk astronomical text, but not in Babylon. Now I'll turn to the Babylonian nothings. Well, how did they deal with the absence of an object, for example, in administrative texts, or with the null result of a mathematical operation? For example, how do you deal with 20 minus 20 as an arithmetic operation? Our zero, our number zero. In older texts, the way you did it was simply to ignore it. You passed over the result, and you either left a blank or you failed to mention it at all. For Old and Middle Babylonian mathematical texts, the situation was avoided in the way that multi-digit numbers were in general avoided. And we only have a single case where it wasn't, once again, interestingly, from Susa, where we have an operation which should lead to a zero result. And we'll look at that in a second. Blanks could be used in administrative texts. That was easier, in a sense, to deal with, and is what was done. So here is an administrative text from Ur-3 again, from Shulgi, year 48 of Shulgi, 2077 BCE, from the city of Girsu, the capital, and the administrative capital, I should say. So we have here the numbers and the objects which are being counted. This is a administrative text about sheep, and we have 13 ewes and no adult sheep. We have 20 male sheep. We have 5 shorn lambs. We have 5 unshorn lambs. We have no lead goats, and we have on the bottom we have the totals. Where you have no, for example, adult sheep, you have a blank here with the word adult sheep written here. Where you have no lead goats, you have a blank. and lead quotes written here. And where the total it gives that were expended to use, no use, blank use, and 2, here's the number 2, male sheep, that you have there. And you can actually see the way blanks are natural occurrences in formularias. Trying to think of what the English term is for these kinds of things. These are the blanks that essentially are the same as the blanks that we already saw for missing sexagesimal digits in the same period. I will just mention this. These are economic texts also from OR3. They are yearly accounting texts where you have a total of expenditures. You have it added up on the back, the very last entry, and then expended with a deficit in this particular case, a surplus in this particular case, and the words deficit and surplus are written out. In this year, you had a balanced account. You had as much going out as coming in, and the total is given here, and the net result is given here. Blank. Nothing. No mention at all, unlike deficit and surplus. And here's that Sousa text I told you about, mathematical procedure text from late old Babylonia. And you have in this line, you will subtract 20 from 20, and from 2, you will subtract 30. Okay, don't forget these are positional numbers, so this 2 is not 2, is 120 actually. But that's written too in Babylonian positional notation. So you subtract 20 from 20 and you subtract 30 from 2. The answer is 130. That is, the answer given is what you get from subtracting 30 from 2. What happened to the 20 from 20? Silence. Where you have the one case where we have a subtraction of a number from itself, we have no mention whatsoever of the result. So nothing really is nothing in Mesopotamia at this point. And the avoidance of putting yourself in a position where you'll have to end up, or you'll end up with nothing in a mathematical text as a result of a mathematical operation comes to an end with the creation of mathematical astronomy in the 7th to 6th centuries BCE, because now we can't avoid it anymore. Essentially, there are astronomical situations in which you are coming down to a baseline in which you have to add or subtract numbers in the construction of zigzag and other kinds of functions, and you need to have that available. Now, expressed explicitly, nothing in the astronomical or mathematical texts of the same period takes the form of a verbal predicate, either negative or positive. Here's a text from Achaemenid period. It's dated, so we know it comes from the second year of the Cambyses rule as king, 524 BCE. Comes from Babylon. It is an astronomical observation text. That is, it is a text which gives you the observations made on a given, for a given month, day by day. And here we have month 12, and on the 12th, for example, the period from moonset to sunrise, and these are the major things indicated on this particular astronomical observation text called the diary in modern terminology, was 10 degrees and 30 minutes. You have the night of the 13th, moonrise to sunset with this given amount. On the 13th again, the time from moonset to sunrise, that's shu, and the time from sunrise to moonset, that's na, was 0. And that is expressed as nutuk. Nutuk is in a Sumerian phrase, although the text was certainly read in Akkadian, a Sumerian phrase meaning there is none. It does not exist. So nutuk, there is none. We'll hear similar kinds of things in Egypt a bit later from our next speaker. Here's another astronomical procedure text, also from the same period, though not dated, so more difficult to determine which between the 6th and 5th centuries, where in between the 6th and 5th centuries it falls. It's a rather complicated algorithm. I won't go into it. What's important is only the end here, the last line, in which you are calculating shu and na again for the sunrise to moonset and so forth for a given period, and this is a prediction, how to predict it, and you arrive at a situation where it has no shu and na expressed as shu and na, la ishu. La ishu does not have. And finally, a text from 328 BCE, the third year of Alexander's rule, Alexander the Great. It is another diary text, and it is given for the 7th month. And here we have again the use of nutuk as a indicator of non-existence for moonrise to sunset and sunset to moonrise, but this time as an observed situation. I have a last text to show you, or almost the next to last text to show you, from Babylon, early Seleucid text from about 300 BCE, roughly, astronomical procedure text with tables, both tables and procedures on the same text. I've taken one part of the table and one part of the procedure to show you. From the table, we have numbers which must be added and subtracted to shu and na, by the way, to create the next shu and na, where you add 4 and subtract 14 on two different parts of your month. For Capricorn, when you hit Aquarius, you'll be adding nothing but subtracting 12. From Pisces, you'll be adding 4 and subtracting 10. So you see nutuk can also occur in tables where it simply replaces a number. It replaces a number, nutuk, nothing. And here in the procedure, the addition is the following. The addition for Pisces is 5. The addition for Aries is 5. The difference from addition to addition, the difference between that for Pisces and that for Aries is 0 for us, yanu. Yanu is an expression which means essentially nothing. So we have finally a resume here of Babylonian nothings with its earliest occurrence known to us now. Of course, that can be turned over tomorrow by discovery of the new text. In the old Babylonian case, nothing, we leave simply blanks. Around 524, there we have an exact date for it. Nutuk comes in, that's the earliest example of it I know in a mathematical or astronomical text. Nutuk is used very often in other areas, and for it simply does not exist. There is no. La Ishu comes in around 500, and around 300 itself comes in Yanu. Now, of these three, Nutuk is the one which is generally used, and it is almost always used during the Seleucid period, aside from this one particular case of Yanu. Unfortunately, we don't know its reading in Akkadian. We only know its Sumerian abbreviation, and it is usually considered that it comes from Uribashi. There does not exist, but it is also used, interestingly enough, in other contexts, other non-mathematical, non-astronomical contexts, to mean la issue, to mean does not have. So its reading as in one or another way is not clear. It's not certain that there are three rather than only two readings for nothing in Babylonian mathematical and astronomical texts. I have one last text to show you. It is unfortunately badly dated, badly preserved. It's an astronomical procedure text from the Achaemenid or Seleucid period. I wanted to only show you one line. In fact, the very first line is the only one that really counts. I put the other two, the following two, in just to show you, because it's broken at the beginning of each line and broken at the end of the line, that what the restoration I'm going to give you is almost certain. If you if you look at what are the other lines in terms of the operations are the same in each line, and we simply only have this part of it. But it's something about days in a month, and then you have 10 ninda, which is 10 degrees essentially, for the calculation of the lunar 4. 10 ninda is its displacement. Nutuk and 10 ninda you will add, and then it's broken. So we don't know what it adds to. I believe, and I think it is probable, that it added to 10. Everywhere else, when you add, you have the answer written down. So that there was an answer written down seems to me clear, and from the other entries, and that it would be 10 ninda, which is the answer, right answer, is also fairly certain. So I think we have here the very first indicator, and the last, because it's the only one we have, of nutuk, nothing, being involved in an actual, as an argument in an actual mathematical operation. So, just to sum up, and I'm running well over time, the material conditions for the production of written text determined in large part the history of the placeholders in sexagesimal notation. From empty spaces adequate for column tables, but creating ambiguity in procedure texts, to the use of a special separation sign to hold the place of the missing digit. That evolution we've seen, first as a purely decimal separation sign, then an extension to the same sign serving as a full sexagesimal placeholder, but not dropping the decimal separation uses of these signs. And we've seen different kinds of choices made, some good, some bad, used differently at different times, used in different places. All of this experimental kind of working with placeholders. And finally, the generalized use of a unique sign, the double corner wedge that we've seen coming in the Seleucid period, and is used for sexagesimal and decimal placeholders everywhere at all times. And the evolution of the expressions for nothing show much the same kind of development. They start off multiple, and they end up only nutuk. They are first a simple phrasal predicate. There is no such and such, nishu and na or do not exist. Then they appear as standalone entries in a numerical table, number, 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 nutuk, number, 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 number. And then we see in the last text a functional argument on the same footing, where the nutuk, the nothing, is on the same footing as a number in an arithmetic operation. And that these two stories, which don't come together in Mesopotamia, are the two stories I want to tell you today. Thank you.
Thank you, Jim. It's, for me at least, too complex to be able to absorb it in one go. I'll have to go over it, the subtleties of it, plus the larger context of how this relates to other developments within Mesopotamian society, philosophically, mythologically, or in other ways that may be relevant to see how possibly they may have arrived at this. What intrigues me is that there seems to be a growing awareness through the medium being used, for example, in this case, clay tablets, that the medium itself becomes significant. I'm not sure yet whether it is a fully conscious development, or whether it insinuates itself simply through use. If you have a clay tablet and you write symbols on it, at some point, whether you're aware of it or not, you begin to see the medium itself as a tool by leaving a space, for example. It's all very complicated. I'm not sure whether we're going to solve that immediately, but it's very, very useful to have this first-hand knowledge. And I'm amazed at your facility with reading those texts. It looks like absolute mumbo jumbo when you look at it. All those signs, to be able to distinguish them and make sense of it. That's really brilliant in its own way. So let's try to digest this and compare it and contrast it to other presentations that we'll be hearing, and then hopefully we'll be having one or two brainstorming sessions to see whether we can arrive at any conclusions. So thank you very much for that, Jim, also for coming in late on recommendation, by the way, of Friedhelm. So Friedhelm, if we may invite you to speak about ancient Egyptian mathematics, because in this context also it serves as a standard of reference for us to be able to discern more about the invention of zero, because the Egyptians, from what I understand, performed mathematics without the need for either zero as a placeholder or a number. So please introduce yourself briefly and then launch into your talk, please.
Yeah, thank you very much, Peter. Yeah, I'm Friedhelm Hoffmann. I'm professor of Egyptology at the Ludwig-Maximilian University of Munich. I'm mainly interested in the later periods of the Egyptian culture and its literature and scholarly texts. Talking about ancient Egyptian numbers means dealing with roughly 3,000 years of written sources. During these millennia, many things changed and several developments can be observed. Ancient Egypt is not the uniform and stable block, which it is sometimes portrayed as. Of course, only a very short Egyptological summary of Egyptian conceptions of non-existence, nothingness, and zero, mainly in a mathematical context, can be given here. The non-existence of something could be easily expressed in Egyptian in the 3rd millennium BC by the negation ni, which became nen in later in the 2nd millennium in this function. One could also use the negative verb tem and say tem when, not to exist. The Egyptian king is, for example, one who makes the foreign countries into non-existing ones. The same expression can be used to characterize things or persons which or who do not exist, are destroyed, or have never come into being. Several further examples are found in the late 1st millennium BC ritual papyrus of the Book of Overthrowing Apophis. There is, inter alia, a long litany declaring that the evil god Apophis and everything belonging to him will not exist. Each invocation begins with, "You will not exist." The only kind of existence left over for this foo is, "You exist as someone non-existent." It is interesting, by the way, to see that non-existence was considered as a kind of existence. In leaving these more philosophical ideas and coming closer to mathematical problems, I would nevertheless like to stress that mathematical expressions are derived from general words and concepts of a culture. In our search for something like zero, one expression became most relevant. The Egyptian language had not only a relative pronoun or relative converter, neti, who is, but also a negative relative pronoun, uti, feminine utet, who not or who is not. The feminine can be used for the neuter, so utet could also mean that which is not. This word, which played a major role in later periods, is attested from the pyramid texts first written down in the middle of the 3rd millennium BC. Already here, the opposition between netet, that which is, and utet, which is not, becomes apparent. Spell 510 of the pyramid texts characterizes the creator god as who says what is, so what exists, who creates what is not. Here again, not to exist is a particular ontological status resulting from a process of creation and complementary to existence. By the 2nd millennium BC, netet utet, that which exists and that which does not exist, has become a common phrase for everything. The word utet also played a role in bookkeeping from the 3rd millennium BC. Objects which should be there but are lost or destroyed, together with their quantity, could continue to be kept in the records under the rubric utet. Although utet and the numbers of the things which are missing remind us of negative numbers, utet does not play a role in Egyptian mathematical texts. In the extant corpus, there are no exercises which make use of 0, and neither did one need a sign for 0 for writing numbers. The traditional Egyptian number signs comprised signs for the units, tens, hundreds, etc. 3020, for example, would be 3 times the sign for 1000 plus 2 times the sign for 20. There was no need to express the fact that there are no hundreds and no units in our example. Since every power of 10 had its own sign and no positional decimal notation was used, like 75, 7.5 or 0.75, no sign for 0 was used or needed, nor for fractions. These principles remained the same in the cursive hieratic and demotic scripts, attested from the 3rd millennium BC and the middle of the 7th century BC, respectively. One should add that in the cursive writings, most groups of units, tens, hundreds, and thousands, resulted in special ligatures. Nevertheless, the Egyptians were able to cope with any calculation within the 4 basic mathematical operations: addition, subtraction, multiplication, and division, without a sign of 0. For the highest numbers, multiplicative writing was common. The sign for 1 million, Egyptian chech, was mainly used in historical and religious texts for expressing the idea of a really high number. But in accounting and in mathematics, the sign for 100,000 was the usual highest number sign. For example, 6 million was written with the sign for 100,000 and the sign for 60 below it. This stands for 60 times 100,000. As one can see, 100,000 was understood as a kind of unit which could be counted. Only the context, however, would make it clear or plausible whether 60 times 100,000 or whether 100,060 was meant. Multiplicative writing for higher numbers is also usual for 10,000s in the cursive scripts. Administrative routine tried to reduce the amount of scribal work. So with the Hecate measure, which was typically used for corn, the high numbers were reduced by using a base of 100 Hecate measures. In the hieratic cursive writing, the sign for 1 and for Hecate Oh, here we are. Mean 100 hecad, while the signs in the sequence 1, hecad and 1 mean 10 hecad. And finally, the sign for hecad and a dot mean 1 hecad. In a similar way, the notation of areas can also be simplified. It makes a difference whether the number is written before or after the abbreviation of the word. These phenomena are at least loosely connected with what could be called a positional writing system of numbers, as the context and the position of a number tell us the intended value. But this kind of writing was only used under specific circumstances and did not form a coherent general system. The different usages of dot and stroke gave rise to an interesting corn measure notation during the Ramesside period, about 1292 to 10,069 BC, in which the non-existence of a number of the higher unit was implicitly noted. This sign here was an abbreviation for the char measure, which consisted of 4 oipe in this period. The number of char was indicated by strokes, the number of the smaller unit, the oipe, by dots. These consistently different number signs made it unnecessary to write the word oipe when it was meant. Thus, this writing here is 2 char, with 2 strokes, char and 2 strokes, and 2 dots for 2 oipe. And this here consequently stands for char, but no number, and 2 dots for oipe. So 0 char and 2 oipe. Probably because dots can also occur in other contexts, one refrained from writing the dots alone. But a clear connection with the corn measure was kept by starting the notation with the char sign. Well known among historians of mathematics is the Egyptian word nefer, which is commonly understood as 0. In the large accounting papyrus Bulak 18 from the Theban royal court of the 13th dynasty in the first half of the 2nd millennium BC, several times one finds the nefer sign. In the accounts, incoming and outgoing goods are listed. In the last line, the balance, literally rest, that is, what remains, is given. This is expressed by the normal numbers. But if there is nothing here, because income and expenditure are identical, nefer is used. It is true that nefer stands next to numbers and seems to be a sign indicating the number 0. Of course, if income and expenses are identical, the remainder is 0. For that reason, scholars take the nefer sign as a symbol for 0. But this goes too far, I think. For nefer, which is rightly etymologically connected with the Egyptian word nefer, good, can also simply be understood as an indication that income and expenses are equal. The account is good. The matter fits. Another word or another use of nefer should be briefly mentioned here, namely nefer denoting the baseline in architecture. A foundation or a wall can be below it or higher. This in itself is not necessarily a proof for something like 0, since the etymological meaning of nefer is simply good. Also, the negation nefer does not imply nothingness. It could simply be a similar use of good, as for example in German, jetzt ist aber gut, it's good, meaning stop, no. In a similar way, the Egyptian verb tem, to complete, seems to be related to the negative verb tem. The perfect state of something prohibits its change and thus produces prohibitive usages of these words. I would like to come back to the notation of nothingness and zero. We had utet, which is not as an expression of things missing in inventory lists of the Old Kingdom. Also, this sign exists in the Old Kingdom in the 3rd millennium, which is either a writing of the negation ni, there is not, or, in my opinion less probable, a shortened writing of utet, which is not. The use of this negation as a mark before some calendar dates is used in the New Kingdom in the second half of the 2nd millennium to make it clear that the day marked in this way was not to be considered that something did not take place or similar, unlike the days marked with a simple dot in the same lists. It is significant that this use of the mark by this sign is only found in continuous lists of days. The system of an uninterrupted list necessitated an entry for every day. Without the basis of a continuous list, it would have been enough to note down only the days on which something did happen. The necessity of considering days with and without a particular event made a sign for not at this day necessary. In a similar way, this demotic sign, literally ush, whole, without, is used in uninterrupted day lists. While, for example, in an ostrakon in the Louvre, different numbers of bunches are given for most days, there are entries which simply say ush, without, meaning there was nothing to record for this particular day. In the early Ptolemaic period, utet, the old negative relative pronoun, surfaces again, this time in the originally masculine form uti, which now was used for both genders. We find it in the context of a mathematical problem. In a papyrus now kept in Cairo and dating roughly to the 4th century BC, it occurs in respect of a pyramid which has a base of 500 by 500 cubits, literally then against ut towards the heart, probably the apex. In spite of some uncertainty, the general meaning seems to be clear. We are dealing with a real pyramid, not with a frustrum. One should note that the text does not say ut cubits or something like this for 0 cubits, but simply without or nothing. This clearly shows that ut is not the number 0, but an expression for saying that there is nothing, meaning that there is no extension at all. Another example of the use of ut comes from the famous field register of the Horus temple at Edfu. The text is dated to the reign of Ptolemy X, who reigned in the 1st century BC, but says that it covers donations back to the middle of the 1st millennium BC and even before that. To understand the text and its relevance for our subject, it is important to realize how the Egyptians used to give the measurements of fields. They were taken as 4-sided areas, rectangular or irregular. The lengths of the opposing sides were added together, the totals were halved, and the two halves multiplied by each other. Of course, this calculation is only correct if the area was rectangular and not irregular. But this approximation was easy, and it was applied in real life. In the case of triangular fields, one simply assumed that one of the 4 sides did not exist. And following the normal way of calculation, the opposing sides oops, here, were added to each other and halved and multiplied with a half of the sum of the other two sides. The Edfu text of the 1st century BC has, for example, ut to 5, 17 to 17 makes 42.5, and thus refers to a triangle for nothing to 5 divided by 2 and multiplied by the average of 17 plus 17 divided by 2 is 42.5. In this case, the idea that it is a triangular area and that one side of a quadrangle is missing is expressed by ut, here the hieroglyphic writing. By the use of this word, it is clearly stated that one side is non-existent. The text does not say that the length of one side is 0 cubits or anything like this. Therefore, ut is used to express the non-existence of a side, not the length of it. The beginning of the text has to be understood as a non-existing side, nothing, opposing a side with a length of 5 units. The same word ut was also used to indicate a missing number. In a hieratic papyrus in Berlin of the 4th century BC and a demotic papyrus in Vienna, probably of the first half of the 1st century AD, a system of 3 numbers is used for a kind of divination. Each position of numbers can have the values from 1 to 9. In addition, ut is used. A set of 1, 1, 2, or 2, 5, 7 are straightforward examples. If one of the 3 digits is absent, the empty position had to be clearly indicated. This is done by this word, ut, in the hieratic text, and in demotic by its demotic form, which looks like this, and which directly derives from the hieratic writing. So then we have in this oracular text 2, ut, 2, or 3, 1, ut. So ut serves as a marker for the absence of a number at a definite position. Again, the requirements of the system make it necessary to indicate the absence of a number. Very similar is the use of ut in demotic astronomical lists, which make use of the sexagesimal notation known from Mesopotamia for degrees and their divisions. The entries in Papyrus Carlsberg 32 of the 2nd century AD consists of 4 positions and have, for example, ut 32, 43, 42, or ut 38, 10, 52, 59. So ut standing in place of one sexagesimal number. I would like to mention that in my opinion, this demotic sign for ut, here's some more examples which show the paleographical variety, was taken over into Greek astronomical texts in forms like these and similar. This Greek sign occurs from the 1st century AD onwards. As far as I can see, it remained restricted to sexagesimal tables and was taken over by Arabic scientists in exactly this usage, namely as a 0 in sexagesimal astronomical number writing. Earlier forms from the 11th and 13th centuries AD are, for example, these here. To the best of my knowledge, the sign only occurs in Arabic astronomical manuscripts within a system of writing sexagesimal numbers by letters. In this system, a sign for the absence of a number was necessary, but not for zero, as for decimal zero, as for example 20 was written with the 20th letter of the old Semitic alphabet, that is Kaf. The overall development in Egypt can be summarized as follows. Already in the 3rd millennium BC, there were words for non-existence, absence, missing, emptiness, etc. There were words for the notation of lost or not existing things in inventory lists. From the second half of the 2nd millennium BC, the possibility of marking whole entries in lists as not applicable can be found. From the middle of the 1st millennium onwards, ut was used to know the non-existence of dimensions, values, or numbers. Thus, that whose non-existence could be written down became more and more abstract. But all expressions, including ut, remained negations, yes, or placeholders, and the step to a number 0 was not made. The demotic sign for ut as a placeholder was taken over by Greek astronomers and finally handed down to medieval Arabic astronomy, but still as a placeholder. Thank you very much.
Friedhelm, thank you very much for delving into this detail, which would elude most of us, just like Jim's would in his context. Again, we will have to digest this and compare and contrast and see whether we can come up with a sensible guideline. But for now, within the context of this presentation, I would ask Jim if you have any questions for Friedhelm, and then Friedhelm if you have any questions for Jim before we go to the panelists. Jim.
Thank you, Friedhelm, for a lovely, lovely presentation. I have a question about the surveyor's formula, what you've talked about for the area of the triangle where you're using ut. In what way would you not allow the operation of addition that takes place with ut and whatever the base of the triangle is, as an arithmetic operation? And if it is a real arithmetic operation, in what way can we therefore deny to ut the sense of some sort of numberhood?
Yeah, thank you. Well, in the Edfu text, the numbers, or rather the dimensions of the fields are given. So the text consists mainly of numbers, and it says maybe west 7 against 5, what did I say? 7 west against 5 east, for example. And 2 north against nothing south. And then the result is given, makes such and such square something. It does not give the working out of the calculation itself. It gives the data and the result. So what I showed to you was my reconstruction, but they do not say 0 or ut qubits. They just say nothing, ut or uted. Yeah. But yeah. To be sure, they also do not say 5 qubits. They only give the numbers. But what I was going to say is, from a text like this, we cannot be sure or surely derive the idea that uted was a number, although it is combined with numbers or in a kind of calculation which derives at a sum, at a result. In my opinion, this fact alone does not imply that UTET was a number. It only, in my opinion, it only says nothing, no dimension. Yeah?
Yeah, I mean, I think that we're getting to the crux of the question about number here, and I think it's very interesting that this contribution to the discussion seems to me to be of great importance. Thank you.
Jim, would there be a comparable situation in Mesopotamian mathematics that you would be able to confirm Friedhelm's reading?
Sorry, Friedhelm's reading of the Edfu inscription, or
of the numberhood of UTET?
No, I mean I gave what I have of the intervention of Nutuk in an arithmetic situation, and I'm not claiming any kind of definite decision on this. I mean, in a sense, I'm, as usual, more radical. I mean, you know, sure, not, and I would say not much longer after as well. But that's something else. I mean, what I'm trying to say is that I don't think that the answer of what constitutes a number has a clear answer without the kind of historical analysis that may not be present for most of the material that we're looking at. Right. So I don't think that there can be kinds of sort of full conclusions drawn, but I think that what is being drawn out here on both the Egyptian and the Mesopotamian side are the ways in which these interactions exist, the limits to which they were pushed by the cultures that developed them, and the question remains open as to the relationship of that to what? To a 17th, to a Bakhshani manuscript period analysis of zero, to a 19th century idea of zero, to my idea of zero, which I taught in my classes. I mean, all this it strikes me as being not necessarily commensurable and with difficulty reconstructible, but quite fascinating in terms of, you know, how far can we go in doing it.
Right. Well, it's good to have this inventory, which we will continue down the line as we proceed, because, you know, it may be the case that we are not able to reach any definitive conclusion, but it should be considered, and as Marina said, elaborated upon. Marina, finally, to the panelists, thank you for your patience. And I had introduced you as a previous speaker on modern mathematics, so we brought you in kind of as a referee on this. If you are able to conclude or say anything to these two presentations from the perspective of a modern mathematician.
Well, first, thank you both. I found them both incredibly fascinating and very, very interesting. So, yes, first, as you said, modern. So, as a modern mathematician, I was very struck by the idea of the triangle as a degenerate quadrangle, which is something we do every day, but I always felt like a segment is actually a degenerate rectangle, and I always felt it was really a 20th century view of things, maybe 19th century. I really felt it was very modern, and here we have it in ancient Egypt. So thank you. I have a couple of small right. So the second thing, which was also very interesting, is here you have something in between a text and numbers. You have these words which serves to indicate something which is a bit like a number. So we saw how in Mesopotamia at some point they started being inserted into numbers, whereas in Egypt they did not. So it's very interesting that there's this sort of continuum between between text and numbers. I had, if there is time, I've just a couple of questions. Is it okay, or do we still have? Okay. So actually, they were both for Jim. Just out of curiosity, these schools, who were the students? I mean, what were these schools of which we have so many documents?
Good question. We don't actually know much about the schools. We have the documents. We have some mentions of schools, but in school texts, so that the degree to which this is a real reflection of school life in ancient Mesopotamia is open question. This is a major problem for work in Assyriology. I mean, in terms of trying to understand how cuneiform culture was actually transmitted, is we have lots of texts and very little context of real Sittenleben of these texts in terms of their use of their public. So this is a question to which I have no answer, and to which all I can say is that they're clearly pedagogical in their structure and in their place, but it is more than that is really very hard to say. There have been recently some works being done on it by other people whom I will be mentioning in my article, but I'll be happy to tell you about.
Marina, can I just jump in here a second? Were there no? I mean, I appreciate that within the context of mathematics and astronomy, there may not have been elaboration on this, but what about the encompassing literary tradition? Is there no mention at all made to, for example, what we're all trying to find out is what kind of device they may have used, or any such reference that may shed light on this? I know from other cultures that there are some indications of that, where mathematical symbolism or at least analogies are made in the literature. So I was just wondering whether that is absolutely, in 3,000 years of history, there's no literary reference to any of this? Jim?
Oh, this is a question for me. Sorry.
Sorry.
My answer is no. There are people who believe that an abacus was in use in Mesopotamia. I have not seen any argument that establishes that in any way. There's no word for abacus in the vocabulary list which we have from a school situation, there simply is that there's no physical remains that can be attributed to such a thing. And there's no mention in schools, in texts in literary texts which speak about life at school, and we have these, and in spite of which I say we know nothing about schools, we have these texts, but they are so clearly written by schoolmasters for learning Sumerian and for learning various kinds of writing skills. But even in these, we don't have any mention of any sort of instrument being used in mathematical calculation.
So how do you think that those tables were composed? The tables that you find, were they done manually?
Yes. But one of the main things of doing tables is that if you do them or you copy them, you don't need to do them. I mean,
but somebody must have made the tables.
Sure, of course, and they can be calculated. And we even have there are various theories about how they were in fact calculated. Once tables exist, they don't have to be redone from scratch any more than, for example, when I was at school many years ago, we used logarithm tables. I never in my life calculated a logarithm. Yet I used logarithm tables all the time for doing calculations. That's the way it was done. We had the tables. I didn't have to copy them. They were printed. But nonetheless, this was a standard kind of thing. In Mesopotamia, unlike Egypt, for example, we don't have many indications of how calculations were done. What we have are saying add such and such as such and such, or multiply, I should say, such and such by such and such. And we have tables that show this multiplication and its answer. So those are the kinds of texts we primarily have. And that is, I mean, once you establish these things, then you don't need to do them again. I'm thinking of the 2/n table for Egypt. God knows these are hard to calculate. But once they're calculated, you just copy them.
Absolutely. No, but that's the point. We're trying to get, like the same thing applies in China, from what I understand. They work with tables and bureaucrats, learn them by heart. So after a while, it's very easy to do arithmetic and possibly more than that. But that is the issue, is somebody must have, even if it was just one person who was able to arrive at, quote unquote, the correct answer for multiplying or dividing or whatever. Once it's established, it's a question of learning it by rote. So that's not the issue. The issue is how was it originally established? There must be ways to do it, also to circumvent zero. For example, simply by taking physical, pebbles or whatever, and doing the calculation and see what happens, and then writing it down, and then forever after just memorize it. That really is the issue, where there are very clever ways of doing that. Rod numerals are very, very clever way of doing that without, with circumventing the use of zero as a number. It was a tremendous breakthrough, but on the other hand, a handicap, because it was such a manual activity that it didn't really require understanding what was happening. Marina, I'm terribly sorry I interrupted you. Please continue if you had any more questions for Jim, and then for Friedhelm.
I had one question, but I guess I probably could get the answer by rewatching Jim's talk. And I didn't really understand the difference between decimal and sexagesimal placeholder. I mean, I think I understand sexagesimal placeholder. You write things in base 16 instead of 10, but so what would be a decimal placeholder?
Sorry, I probably not totally clear. The decimal placeholders are the use of the same sign as for sexagesimal places, but used where there is because of the additive nature of the construction of sexagesimal place, you have tens and you have ones. If you have no ones and you only have tens, then you can write it, that number of tens, separation sign, and then the next digit, the next sexagesimal digit. Same thing, obviously, with the no tens, but units. You write the placeholder, the units, and you carry on. These are what I call decimal, because they come out of that 610 construction that is additively used for building up numerals, building up numbers in cuneiform writing. And they are used, and they mean that, and they serve because they separate out possible, very often separate out possible misunderstandings. If you have tens, no units, tens, then you might read those, and you write them close together. You risk reading all the tens together as one part of a 20 plus a 20, and then you have 40. So then you write that down as 40 and go on with the number. I mean, that's wrong. You have 20, and then you have 20 something. So the signs serve, the decimal placeholders serve to indicate the non-existence of units or tens in a given sexagesimal digit.
Is that clear, Marina?
I think so.
Yes. What occurs to me is that being so early with their mathematics and their astronomy, it's fabulous that they managed to do even that. but it is still a mixed system of additive and multiplicative plus positional, which is sort of like a transition between, you know, us knowing where we want to go eventually to the positional decimal system with 0. It's a way of doing things that isn't quite yet as sophisticated as it will eventually turn out to be. So in that sense, it's very brilliant. But in connection to that, I'm just wondering, before the introduction of the placeholder in the sexagesimal system or the decimal system, before that was the case, are there tablets prior to that where you have something that is not yet a decimal system with a placeholder? Is there a sexagesimal system without a placeholder?
Again, me.
Jim?
No, there can't be. There can't be.
There can't be.
There can't be. If you
Okay.
have a hexadecimal system and you have more than 3-digit numbers in that system, then you are going to have to somehow indicate the falling out of the middle or of an internal sexagesimal place.
So the question is, the question is, what was there before? How did they?
You didn't have a sexagesimal system before.
What did they have?
You had a number system which was embedded in metrological systems. You had numbers.
What was that like?
For example, in the earliest writing period, around 3500 BCE, you don't have, for example, you don't write 14 sheep and 14 units of length in the same way. 14 units of area, I should take that as that case. 14 areas of units of area and 14 sheep are not written to the same 14.
Ah.
Okay,
but how were they?
You have numbers which are embedded in a metrological stratum.
But what were the numbers like? What were those numbers like?
They used a repertoire of about 7 or 8 signs, organized in different orders for different kinds of measurement: area, volume, length, discrete objects. You arrange them in different orders. They had different ratios between them in the different systems. So that this very same sign in one system would have one value and another system would have a different value. So but you would know what system you were working in because you were writing the stuff down. So in that system, you would arrange the order of the signs and their values in the correct way.
So within the context of Mesopotamia, it was a huge breakthrough. How did that happen from that metrological system to the hexagesimal system?
There is a number of things written about it. I've written about it. Other people have written about it. So it's there's a large literature. I would say there is no universally accepted answer to that, but I like my answer, which I've written about elsewhere. But that it comes from the metrological system already. Otto Neugebauer saw that in the 30s, and I'm totally in agreement with that. And I think I know how it came into being in terms of the kinds of reforms of writing and of administration, which were involved in the transition from the Sumerian to the Akkadian empires around the introduction around Sargonic period, and the ways in which the reforms in writing generated a kind of ambiguity in trying to use the old systems, the old metrological systems, the ways in which this led to, in fact, by reduction, by these sorts of pressures, and by the simplifications that were involved in the various reforms, leads to essentially an automatic sexagesimal system.
Interesting, because
I think much later in history you have the same transition from like volumes, measures of volumes. There was it depended on the volume of what you took, and so to now we have a single unit for volume. So there was the same transition.
So that's in itself a very, very fascinating moment of innovation within a culture. And contrary-wise, what I imagine is that culture can work against it. If a culture is so strong that innovation is not stimulated, if scribes are not encouraged to innovate, but simply to repeat what they've learned, and then that tends to have a kind of an inertia that'll work against innovation. So I think from what I sense from what you're saying is that it's precisely, again, when there's a transition in culture, for example, when one nation conquers another, it seems to be a moment of innovation when people rethink what they've been doing or try to accommodate it. So, but that's a separate issue, although it is related to eventually the use of zero, the slowly bringing in of the placeholder and then symbols for that, and then eventually recognizing that as having to be integrated into the larger mathematical astronomical context. I don't know whether we're ever going to disentangle that, but this is a good start to at least get a clearer picture of what we're talking about. Marina, any wind up from your side?
No, just great lectures and food for thought.
Okay, thank you very much. We still haven't got your view on whether, in your opinion, there was a moment when the number zero was invented. What would you say is the one bottom line distinction between what is the minimum criteria for for zero to be a number? Could you say anything about that, Marina?
No, I mean, what we heard today makes me think more and more. I now understand more. I see it more as a continuous process.
Right. Continuous process. Yeah, that seems to be where we're heading, also from what Jim has said. Okay, we have a very late joiner. I don't know if he's still with us, Kevin. Mayank Vahia from Mumbai.
I'm here.
Mayank, are you with us?
Yes.
Oh, wonderful.
I am. Wonderful. And I've been patiently listening to these wonderful lectures.
Well, Mayank has a special overview of this from the Indian perspective. He's an astronomer by trade, but has delved into many areas and tries to connect those, which he will do in his paper, Connecting the Zeros. Mayank, what is it that you observed?
So I think I just want to make a couple of quick comments. So hexadecimal system comes simply because it is easy to multiply by multiple numbers. Am I right? You can divide it by 2, 3, 4, 6.
Sorry.
So it was convenient for dividing material in the market.
It's not the reason the system came into being.
Then what is the primary reason for coming to base 60?
That's what we were talking about that just a little earlier. I've written about it, and I'll be happy to send you the article in question. Okay. I have, at least my position on how that came into being.
Because it's an odd number system to have. And you said it is not astronomical, and you said it is not trade related.
No, it's metrological. In origin.
Metrological. Okay. And Friedhelm said that they counted zero as good, which was an interesting representation of this. If something was balanced out, they called it good instead of zero. And it's an interesting expression for zero is what it struck me as most. And that's about the only comments I have. It was quite fascinating to see both the presentations. But I still think that both were strictly numeric in structure, arithmetical in structure.
You mean in Egypt and in Mesopotamia?
Both, yes, Egypt and Mesopotamia.
So the same question to you, Mayank, because I know you hold a view What is the distinguishing characteristic, in your opinion, between a placeholder and a number?
Number is used, the placeholder is simply a number that is used for convenience. Zero as a number is something where you play with the number as an entity. Try and add it to others, try and subtract it to the others, and wonder what happens. The curiosity of using zero as a number with which you operate independently is, I think, what distinguishes zero as a number and zero as a placeholder. Placeholder is simply a question of convenience. You use blank, then it got confused, so you had this double edge. But you didn't play with that number zero, saying that, look, if I add, if that fellow has 5 cows and if I add 0 cows, it still remains 5. That curiosity was not there. That is my personal feeling.
So what moment in history do you see that this changes? To
me, it's a lazy man's invention, in the sense that when the culture was relaxed enough to, go beyond simply the arithmetic of numbers and go into algebra, is when you start dealing with zero. So it is because it is not utilitarian. It doesn't become utilitarian until much later. Early uses in arithmetic and even in business, and even Chinese, for example, use to solve linear equations without using zero. So you could do a lot of arithmetic and business-related arithmetic without using zero. So zero to me is an armchair invention by somebody who was just curious about how come if I add zero to something, it remains zero. Or if I take away everything, can I divide zero into fractions or something? To me, it's an armchair invention.
Very good. I like that. Jim and Friedhelm, we haven't talked about that. Was there any semblance of algebra in either Mesopotamia or in Egypt? Friedhelm, we've heard less from you.
Yes, there are several algebraic texts from Egypt. Divisions of numbers, calculation of volumes. Oh, what's the word from volumina, and any such things, calculating areas, but they did not. And sometimes perhaps even what we would call equations with an unknown number, but they did all of it with words, not with symbols.
Jim, algebra in Mesopotamia?
No, and I don't believe algebra anywhere until much, much later. So that's no.
Okay.
I think Al-Khwarizmi himself, he wrote using words.
Sorry?
I think, indeed, much later, I think Al-Khwarizmi himself, when he wrote a treatise about quadratic equations, he only used words and sentences.
Al-Khwarizmi, okay.
So symbols are a much, much later story.
Yes.
Okay. Mayank,
yes.
Algebra in India?
Oh, algebra in India is 5th century AD, Aryabhat. That is when they start really speculating on how to have variables and stuff like that, going beyond linear equations. Till linear equations, I think it is a trade-related development and working on series. So Indians have these problems that they were worried about making these fire altars with similar area but different shapes. So they had to worry about fitting a square and a semicircle with the same area, because the 2 different gods with 2 different fire altars had to have the same area so that none of them felt insulted. So the early mathematics algebra in India is just trying to fit a circle to a square. And then the problem with pi comes in and a whole series of problems come in, because pi is not rational. So they really struggle to have a circle and semicircle especially and a square with the same area. So that, I think, is where for the first time non-linear algebra comes in.
But Mayank, 5th century, the fire altar thing you're talking about
are very old. Yes,
that's very old. And so would the same thing hold that Marina just said, that they used words to calculate?
No, they had series. They had series functions and all that. But still, Yeah, they did that series. So they would try and fit it with, take a semicircle and put a square in it, then try to subtract the side of it, then do an infinitesimal size square rectangles and try to fit into the sphere and worry about the area and stuff like that. But it was all numerical analysis. It was not, as far as zero is concerned, it was not involved there. And they were just, so there were series equations, etc. But they never put zero is equal to zero or stuff like that. The real curiosity comes in when you start completely abstracting beyond linear equations, and then you start worrying about, look, this zero is a curious entity, how do we handle it? So but the early mathematics in India is this fitting the square to a circle. So there are series equations, there are worries about pi and so on, and Pythagorean triplets and stuff like that, but there is no zero. I mean, zero in the sense of decimal number is there, place value is there, powers of 10 are there, etc. But this beautiful play with zero as a number and trying to see how it goes around with other entities. Why is 0 plus 0, 0 plus a number 0? Why is 0? Why can't you divide by 0? And why can, if when you multiply with 0, you get a 0? Those kind of curiosities are 5th century.
But how would that be different from what Jim and Mayank have said, that this evolution of the concept of nothingness in Mesopotamia and in Egypt, that nothing means nothing, and the Islamic world got Aryabhat, or rather Brahmagupta's work, and if Brahmagupta had seen zero as a number and as an invention, the Arabs did not take it over.
Yes. So they also missed that subtleties because they were more rationally minded. That's what I'm saying, that it's something, if you're studying relax and curious about numbers playing with each other, is when you would first worry about why 0 multiplied by something. For example, Aryabhat himself doesn't do that. It comes out slightly later than Aryabhat's original work in mathematics.
Right.
So I think it's something, a sort of more abstract level of thinking of mathematics that brings it in. Up to linear algebra, it is still arithmetic, business arithmetic essentially. But this idea as to why 5 into 0 is 0 is an abstraction level.
Right.
And Indian algebra has a geometry and algebra arithmetic fixation in the early stages. That is from Vedic period, where they try to make Vedis of the same area. And so you end up with this series because you're trying to make smaller and smaller square and trying to fit in. And then you worry about trying to see if you can do arcs and stuff like that. And then these Vedis are shaped in a particular manner. So you need Pythagorean principle to get your shapes done through string and string in a mud, as it were.
Right.
So those things they have.
Yeah.
But not this lovely play with zero as an entity.
We're gonna have to really outdo ourselves to harmonize any and all of this.
So I'm talking next week. I'm going to make this point that this idea of playing with nothingness is what contributed to the idea of studying nothingness in mathematics, because mathematics was treated as a language beyond a certain point.
Right.
And then, like the completeness in Greek, in Egyptians, where if nothing remained, it was called good rather than something that was to be alarming, but something that was to be happy about. That kind of an attitude is where things would change and people would start getting interested in zero.
Okay, so absolutely, we will announce your presentation at the end of this. Okay. Look forward to that. The Friedhelm, Jim, and of course Marina, if she would like, are welcome to join in on that's on the 20th, Sunday the 20th, to take this discussion forward, to see whether we can get beyond this at the present, this sort of like this jumble, and see whether we can arrive at anything, or whether we have to leave it at that and just simply accept that this is what happened in history without getting a clear answer to our curiosity. But so thank you all very much for that. For now, I would like to give Jim and Friedhelm a shot at how we conclude all these sessions with a very brief survey, very quickly, one-liner, no more discussion. Please reply in a single sentence to the following 3 questions. We'll go with Jim first and then Friedhelm. Was the numeral 0 discovered or invented? Jim.
Invented, as all concepts are.
Friedhelm, was the numeral 0 discovered or invented?
I really don't know. Perhaps
Okay.
it was discovered, yes.
That's fair, that's fair. Second question, was the transition between the placeholder 0 and the numeral 0, which we've been talking about, a gradual evolutionary process or a disruptive moment in history, Jim?
Very gradual process.
Okay.
Still going on.
Friedhelm?
Yeah, I too think it was an evolution
process. Okay. And then finally, you know, harping on our working hypothesis for the time being, is the concept of nothingness or emptiness, is it trivial or profound?
No idea is trivial. Whether one idea is more profound than another, I couldn't say.
Okay. Friedhelm, the concept of nothingness or emptiness, is it trivial or profound?
I think it's trivial.
Okay. There's no more to it. And it probably, that case probably may not have played a role in the invention of 0, as Mayank was suggesting. Okay. All right. We'll leave it there for now. Thank you again for joining. This, you know, hope it didn't spoil your Sunday afternoon. It certainly didn't ours.
Yes.
We've been looking forward to it for a long time. Speaking to the virtual audience, please join us again the week after next to explore related issues to pinpoint, if possible, Zero's epicenter. We will then meet, as mentioned, Professor Mayank Vaya on connecting zeros. It's a wide-ranging interdisciplinary perspective. Thank you. Until then.